Thank you, Session Chairs. I'm very happy to be here. It's first time for me to be in Athena or in Athena, and I think it's very beautiful, and I like my stay so far here. I'd like to present our work, Low Cycle Fatigue Life Assessment of a Gas Turbine Housing, which was contributed by my colleagues from my faculty, University of Zagreb in Croatia, from University of Rijeka, and also from University of Belgrade from Serbia. So after a brief introduction, I will explain our low cycle fatigue model, and then we will see finite element models and analysis, and we'll discuss results and draw some conclusions. Here you can see gas turbine housing of a large industrial gas turbine, and it's not a secret, it was Alstom gas turbine GT26 and very similar to GT24. So you can see it's very complex geometry, and this structure is exposed to not only mechanical loads but also to thermal loads. So, and cracks can appear even where we don't expect them at all, not due to service mechanical loads, but due to thermal loads, which are somehow not expected or not expected at that locations. You see that we have many stress concentration sites, and from here we have compressor, and after that we have exhaust housing and electricity generator. So it looks like this, but it's actually all the setup is very, very long. So what actually we see here, we have cut of the gas turbine, and we see that we have some parts which are needed to support other parts like vane carriers or blade carriers. So and they are not heavily mechanically loaded, but as you can see, this we have some parts here. Here right now at the last stage of compressor. So turbine is here. Here is compressor. Temperature is not very hot. It's cold air, which with temperature 550 degrees, and later it becomes hot. But 550 degrees is still a lot for these parts here, because during startup they see warm air, they try to expand, and during shutdown they see cold air and they tend to shrink, and we will see that due to this in service cracks were observed, like see 50 millimeters here crack, or here crack, or here. And then also we have some other examples. This is at the side, so we have cracks like this. And naturally, when gas turbine owner makes regular check, so he is asking why do this crack occur and how critical are they from structure integrity point of view. Maybe they are not critical at all, but anyway, it is needed to say about it, but they may be critical. So what we need to do low, and what I forgotten to mention, that was observed very early during the first 2 years of usage, maybe after less than 50 cycles of operation, and normally one gas turbine should experience 2,500 cycles. Maybe that was standard 15 years ago, and today 10,000 or 20,000 cycles. So this is typical loading history. So we have startup, then we have some variations here depending on output of electricity power, then we have shutdown, and again startup, and so, and this is one work loading cycle. And to model this, we need to give good data about startup, shutdown. This is for then mechanical loads, this is for temperatures, and so on. So we have to simulate one startup, steady state, shutdown cycle. And also what can happen that creep can occur here. We have not considered this. So normally in gas turbine industry, what they do, they have a component. This component is loaded for a blade that is centrifugal load and hot air with temperature and pressure, and we also have cooling coils here. So the same procedure is applied to all gas turbine parts, including gas turbine housing. So first is done linear analysis. So we calculate transient analysis, we calculate nodal temperatures and nodal stresses. Then this is transient process, so we have to identify from this stress range which is applied, which each node see, and also we have to take into account temperature effects. So we normally do linear and stress analysis, linear structure analysis, because we can oversimplify it, like Norbert rule procedure, get strains, nonlinear strains. Because plastic analysis takes a lot of time and we have to repeat many times, then we are not efficient. And at the end we need what is very important, material data. We need epsilon n curves for the considered material. So we speak about low cycle fatigue. I mentioned Norbert rule. As you know, Norbert rule is it's well known and it's very convenient. So from linear elastic analysis like this, we can reconstruct elastic plastic stresses and strains if we know elastoplastic material behavior. So basically what Norbert is saying, that area of this triangle is equal to area of this triangle here. And then we can see that actually area under this nonlinear curve is this. So this procedure is conservative. It's conservative and we can use it. During the transient startup shutdown cycle, we have many points which we model, like 15 or 20, and we have to see the worst combination of all this transient effect which will give the highest stress range, and this range is relevant for our fatigue life assessment. So this is material data. We have epsilon n data, but since we are doing a linear analysis, we transform by Norbert rule this to stress range. So we have unrealistic high stresses. Of course, this material cannot, but it carry that high loads. But we can use this data for we can combine them with linear stress analysis results and determine fatigue life. So for these sites which we have seen before, for these supports, to get an answer how many cycles do we expect to crack initiation, we have to do finite element modeling. We use global model, and we also do sub-modeling for our parts of interest, like here. So we take from here temperatures and stresses and use them for local model. Here you can see temperatures, and we have to, apply thermal boundary conditions, temperatures. So I mentioned 550 degrees in compressor region, and also we have to apply mechanical loads, pressures. We have pressure on these flanges here because of contact of vein carriers, because it's so. And actually, these mechanical loads are not very high. They do not load these parts much. You see that transient temperatures are the reason of cracking, which we have seen before. So we need to apply boundary conditions, transient boundary conditions, as I mentioned before, and for temperatures, for mechanical loads. And since it's, we speak about some modeling, we have here symmetry boundary conditions, and we have here driven nodes. These nodes take results from the global model, And at the end, we get number of cycles to crack initiation. Number of cycles to crack initiation. And we did our analysis very carefully, modeled boundary conditions to our best understanding, temperatures, heat coefficients, intrinsic, and all other data, and we got this. You see, 12 cycles to crack, 26, 37. Maybe it's not 12 cycles in reality, but it's telling us that it's very low number of cycles. And this is in very good agreement actually with what we have observed in the experiment. And I mentioned that we have several time points. You see that very high compressive stresses occur due to start up, and here we have some stresses during shutdown, and they define stress range. And this range is very high. Consequently, we have very low number of cycles to crack initiation. So what was the problem? Problem is, as we know, when we have stress concentration sites, they are not good. We always want smooth transitions from one area to another. And in our cases, we had cracks here, and here, and here. So we smoothed this area here, and this part even was cut so that it can move, you know, that we don't have stress. So then we also, for this modified design modification, have to carry out analysis, and people from industry, they like to apply heat shields like this, although they are not helping much. More important is stress concentration. So similar, we have models like this, apply boundary conditions as we applied before, but we model here new temperature boundary conditions, and geometry is different, loads are same, and then we have fatigue life for this. We remember it was before like 10 or 20 cycles, we extended fatigue life for 100 times. So, and so that this is significant improvement. And stresses are stress range is much lower now. And then maybe I was a bit fast, but we can enjoy our coffee break better. I just go to conclusions. That high compressive stresses occur at stress concentration sites due to transient thermal loads, not mechanical but thermal. So these thermal loads are really can be very devastating. Thermal stresses at sites of geometric distribution have caused fatigue cracks, which were observed in regular inspections due to low cycle fatigue. By reducing stress concentrations and also by applying heat shields, fatigue life was significantly improved. So I hope that you enjoyed this real case study from industry. And you have my data here, but I don't give up so quickly, you know. I want to show you that we are organizing a very nice conference in September in Dubrovnik, and you are probably all of you have already seen and get flyers, so please join us and distribute information among your colleagues. Thank you very much.
Thank you.